This is our presentation on electrolytic oxyhydrogen generation to drive energy savings and guide operations horizon. I am Kyle Dupre, joined by Sean Mayfield, Flobert Akapu, and Timothy Perry Mills, and we are Bright Solutions Consulting. Before we get started, here's a brief overview of the presentation. First, we will introduce the problem we identified and the process that we designed. Next, we will go over the main components of the process, the electrolyzer and the boilers. Then we will describe the model we created to forecast the gas usage of the boilers. Next will be our feasibility assessment, followed by some of the safety, control, and environmental impact considerations made before giving our final recommendations. First, an introduction to the problem that we identified. Every year, the Yuengling Tampa Brewery produces around 1.1 million barrels of product. This requires the purchase of over 100,000 million BTUs of natural gas annually, which in the past several years cost under $600,000. In 2023, it was observed that the brewery paid around 30% more in natural gas than in previous years. This can be observed in the figure, with the most recently monthly rate for both the TECO and the Infinite Gas services shown by the filled-in diamonds, which are tan and yellow, respectively. As you can see, the prices have become volatile in the recent year or so. According to the EIA, while the Henry Hub shows a low for the national average natural gas price, they announced in their February 2024 short-term energy outlook that demand is expected to grow faster than supply in 2024 and 2025, as it did previously in 2023. By leveraging these rising costs, our project aims to save the brewery over $100,000 in natural gas costs each year, while also striving to anticipate changes in industry practice to come. The 2022 United States Inflation Reduction Act directed close to $400 billion in federal funding for clean energy projects. Natural gas is a limited resource which is recovered from petroleum extraction processes. It primarily contains methane, but also other elements including ethane, propane, butane, carbon dioxide, and more. When we combust natural gas for its heat energy, the products are released to the atmosphere in the form of flue gas. This can release not only a great amount of CO2, but sulfur and nitrogen oxides as well. These compounds are highly damaging to the Earth's atmosphere and ecosystems. As part of interglobal efforts to reduce the carbon dioxide emissions across industry, natural gas is being targeted to be phased out in use. This is to be done through electrification for smaller heating units or by replacement with hydrogen where combustion cannot easily be replaced by electricity. To sustainably produce this hydrogen, electrolytic water splitting is preferred as it can be powered by sustainable energy from solar, wind, or hydroelectric sources. And introducing renewable energy to the hydrogen production process not only promotes the economic feasibility of this project, but also the further decarbonization of heavy industry. For our design approach, we first investigated the technical aspects of the problem. We compiled any existing studies, reactions data, and information related to this as possible. Next, we used this information to determine which experiments we wanted to perform and what data we were interested in from them. After this, the team was able to synthesize a base design for the oxyhydrogen production system and detail how it would interface with the existing process units. Using data provided by the brewery, we constructed a gas usage model which would allow us to forecast the brewery operations and perform an economic feasibility study on profitability of the project. Finally, the base design was optimized to be profitable, reliable, and safe for both the facility and the environment.
My name is Flobert, and I'm going to talk about our project challenges. First, integrating a continuous process with a batch process The boilers operate to support main operations, and fuel demands are high when making batches. Understanding the day-to-day brewing operations. Oxyhydrogen fuel systems without storage needs. Designed to meet the production criteria, the system must always maintain safe, appropriate heat value of fuel required by the boiler. There are limited literature on the topic. Oxyhydrogen combustion, it's a new emerging technology. Photovoltaics can be inefficient and occupy large space. Considering these challenges, this is the solution we came up with represented in the block diagram.
I'm Timothy, and this is our process details. We assume that all substituted fuel will be replaced with oxyhydrogen with no effect to boiler operation. For the boilers, we assume that steam operation is consistent with the provided data and that fuel requirements and all technical data match the manufacturer's specifications. For the electrolyzer, we assume that it would be powered by both solar energy and grid-provided electricity. Finally, the boiler was modeled using the Penn-Robinson equation of state, the electrolyzer was modeled using electrolyte NRTL, and stream conditions were determined from given data, stated assumptions, and ambient conditions. This is the process flow diagram showing how the electrolyzer will be integrated into the current boiler system. This process represents multiple boilers in one, labeled B1. The most important streams from the flow diagram are summarized in the table. Stream 1 from the diagram is the feed water for the electrolyzer. Stream 8 represents the oxyhydrogen generated by the electrolyzer. Stream 10 is the air feed for the boilers. Stream 12 is the natural gas feed line. Stream 13 is the combined natural gas and oxyhydrogen fuel line. Stream 14 is steam flowing out of the boiler shell. Stream 23 is the boiler flue gas, and stream 25 is the feed water for the boilers. The flow rate for stream 1 was calculated based on the value that we calculated for stream 8, along with the efficiency of the electrolyzer. Streams 10, 12, and 13 are modified from manufacturer specifications to account for the addition of oxyhydrogen fuel. The steam flow out, flue gas, and feed water specifications are all per manufacturer for 2 boilers operating at 100% capacity.
Hi, I'm Sean Mayfield, and I'm going to talk about the last slide we have here in our process details section, which is the individual units. Just a quick breakdown of them. The first one we have is the electrolyzer, which is really the heart of our project. It had an internal water flow rate of around 3,000 pounds per hour, and we had varied the required power for the electrolyzer between 150 and 200 kilowatts. And our boiler, which Yingling provided data for it, there were 2 of them, CB fire tube boilers that we had in our model, which each had a max steam output of 26,900 pounds per hour and a maximum fuel input requirement of 29,000 BTU per hour, which for natural gas works out to be 1,469 pounds per hour. And it also had a required heating power of 800 horsepower each and a heating surface of 3,500 square feet each. And now for this next section, we're going to break down the electrolyzer. And as a general overview for our electrolyzer design process, we had 3 different commercially available kinds of electrolyzers that we could choose from: proton exchange membrane, alkaline, and solid oxide. And ultimately, alkaline electrolysis was chosen due to the greater energetic efficiency and lower costs associated with the mechanism. And potassium hydroxide was the most commonly used electrolyte due to the lowest likelihood of side reactions like the potential generation of chlorine. And water flows through the center stack at high velocities and goes out to the gas separators where the hydrogen and oxygen can both be purely separated from the water. and the water is about 28% by weight potassium hydroxide, and the reactions here, at the cathode hydrogen is produced and at the anode oxygen is produced. Now, when concerned with modeling the electrolyzer, we started with Aspen, which was to just get a general idea of the scale that we would be operating at, as well as understanding the required circulation flow rate and the feed water flow rate for the electrolyzer when running it into the furnace. And we also modeled with COMSOL. We could only do single cell modeling due to the required time frame that we could only model within. And we mainly aim to model gas dispersion inside of an individual cell so that we could get the plate spacing between each of the cells, and then we could generate a stack efficiency from which we could scale the overall electrolyzer model with.
I will now go over the boilers in more detail. This is an overview of the two newest boilers purchased by the brewery. They are Cleaver Brooks 800 horsepower, 4 tube pass, fire tube, steam boilers, and handle most of the brewery's steam demands. They are designed to operate at 125 psi and are programmed to fire at 4 different combustion settings. These are important as they are the basis of the gas usage model. Each level has a maximum steam output and corresponding fuel requirement. The boilers are configured in a lead-lag control scheme, where one is fired to handle the main load and other engages when the steam pressure is detected to drop too low. These boilers supply steam for brewing as well as cleaning and pasteurization. While it was not used for modeling purposes, the brewery also employs the use of their older water tube boiler, especially on weekends and other non-brewing days. This is a Volcano Tech 600 horsepower water tube boiler equipped with 2 1.5-inch steam drums and 1 2-inch steam drum. The manufacturer's specified steam output was obtained by the documentation provided and combined with the boiler's inspection data to estimate the fuel requirements based on enthalpy change of the water and efficiency. This boiler can also be configured as a lead or lagging in the control system and is supported by the fire tube boilers. Because less mass of water is contained at one point in time in a water tube boiler, it is an inherently safer design when potential energy release is considered. For the boilers, it was important to understand how the temperature of combustion would increase when hydrogen was introduced. The composition of flue gas would also change, and so Aspen process simulation software was used to study this. The reaction was first modeled using a Gibbs free energy minimizing reactor in Aspen. Then, the Arrhenius parameters for combustion of the components of natural gas were obtained and used to configure a plug flow reactor that more closely represented the conditions to the boiler. This increase in temperature was found to be under 100 Celsius degrees for the volume of hydrogen we would consider adding. Under complete combustion conditions, the carbon dioxide emission reduction is roughly proportional to the amount of natural gas which is substituted. Knowing the increase in adiabatic flame temperature, the boiler was roughly modeled in COMSOL to understand how this would affect the overall heat transfer of the exchange surfaces within. I will now discuss how we modeled the gas usage of the boilers. Here is a brief overview of the approach taken to synthesize a gas usage model based on the data provided by the brewery. The provided gas usage data gave an idea of how natural gas prices change over time. We looked at the difference in gas usage for brewing days versus non-brewing days, and it was observed that the cost of natural gas varied over different periods of a year. The brewery produces different volumes of product over the course of a year based on demand and the status of other Yuengling breweries, and this pattern was incorporated into the model. The steam production data gave us a more zoomed-in look at the minute-by-minute steam demands of the facility. Here, the lead lag control system of the boilers was studied and reproduced for a model week of brewery activity. Each day of this week was broken down into 10-minute intervals, and the expected average steam requirements were estimated. Only steam data for brewing days was provided, so the off days were approximated to forecast the average amount of gas that was reported to be consumed on these days. And finally, to assess the validity of the model, the cumulative gas usage in the steam data was broken down into similar 10-minute increments and compared to the model forecasted values.
So when generating a model for our data, we first use steam data provided to us by Yingling on 3-day periods for 2 different weeks, and we broke that down into 10-minute increments. And then we also used natural gas data provided to us by Yingling for trends that they had paid on daily and monthly bases over the years. And from that, we generated a plot using the real-time gas flow meter data. And then we aim to replicate that pattern using boiler operation patterns by changing the combustion settings. So after we had analyzed our benchmark, we had then created a model from the different boiler settings that we had then compared back to the benchmark and performed an error analysis so that we could further optimize our model. And as a brief overview, we found a median error in the model of 9%, and then if we had the accuracy set to within a 12% error, 95% of the data points were in that. So we used that information to scale the boiler so that we could account for any error or further usage within the electrolyzer.
In this section, we're going to talk about economic feasibility or economic assumptions. The model capacity trend is constant each year. The revenue is based on incremental savings on gas usually modeled. 17.5% natural gas used at any time will be substituted. The natural gas cost of $6.59 per thousand cubic feet based on the average of 2022 and 2023. The electricity cost of 11 cents per kilowatt water, it's the average quoted by brewery. Operating costs covered by electricity when solar panels not operational. The working capital is negligible and it is handled by the maintenance cost. The electrolyzer length factor of 1.12. We use max of 6-year depreciation. The minimum acceptable rate of return is 10%, and the acceptable payback period is under 5 years. The electrolyzer total was $280,000, including 2 units of 150 kilowatts. The 200 kilowatt solar panels was $200,000 and occupies 8,200 square feet. The stainless steel pump was $3,000 and the 50-gallon chemical tank with the pump was $4,000. The pipe and fittings cost $5,000. The material chosen was stainless steel for the electrolysis fluid and carbon steel for the remaining. Control valve, sensors, and wiring was $3,000. And the total equipment cost was $495,000.
Our operational costs are as follows. The average annual cost of electricity not supplied by the solar system is around $35,900. The annual maintenance cost of $750 accounts for 2 electrolyte refreshes and a yearly preventative maintenance. Using the model discussed, the amount of natural gas replaced was used to estimate the annual fuel savings, and the cost of electricity was based on the energy required to produce enough oxyhydrogen to replace the natural gas. These values, along with the economic assumptions listed, were used to estimate the feasibility of the project.
So for our cash flow study, we used a solar tax credit as well of 30% of the capital investment for solar panels paid over 10 years, and we optimized the purchased electrolyzers to run near max capacity while the plant itself was also at near max capacity to minimize the amount of natural gas used. And when analyzed, the project is profitable until uncertain values approach the pessimistic levels. And then to reflect on that, the natural gas prices have a larger effect on the NPW and payback over the electricity. And one thing to note is that we have these dashes here because we did not co-vary both the natural gas and electricity prices, so we just have a pessimistic case and optimistic case for both respectively. And here we have our final cumulative cash flow diagram. On the left side, we have natural gas price uncertainty, and on the right side, we have electricity cost uncertainty. And from the black line, you can see that in the pessimistic case, the project barely pays itself back over the 10-year period we analyzed. However, when we move to more optimistic cases, the NPW improves.
Now we're going to talk about the environmental impact. Our project reduces the use of non-renewable sources, as well as reduce the direct CO2 emissions. All the carbon-based fuels that are released into the ozone and damages the atmosphere. Adding solar to the process reduces the emissions from natural gas power plants.
Now we will discuss safety and controls. Hydrogen is lightweight and burns readily, making it prone to vaporizing and forming a vapor cloud. Using the CRW-4 chemical interactions tool, co-developed by the American Institute of Chemical Engineers, the Emergency Response Division of the National Oceanic and Atmospheric Administration, and the Office of Emergency Management of the EPA. When mixed, oxygen and hydrogen can produce products that may be explosive, flammable, unstable at room temperature, and may be violently explosive. The reaction of oxygen and hydrogen is also exothermic. Oxygen and methane also can react exothermically and produce products that may be flammable, violently explosive, and toxic. We recommend fail-close valves for both the water feed line to the electrolyzer and the oxyhydrogen fuel line. Plastic piping should be avoided for carrying oxyhydrogen to avoid static shock since it is a potential ignition source. Finally, there should be more than one flow meter for the oxyhydrogen feed line to detect deviations in flow to allow for the use of a voting system. This is the P and ID for the process.
Lastly, we have our conclusions and final recommendations.
In closing, the team recommends proceeding with the designed oxyhydrogen system. The total capital investment would be $555,000. The payback period is 4 years and generates a 20.5% return on investment in the first year. The incremental discounted rate of return is 16.7% based on a minimum annual rate of return of 10%. The system is low maintenance and flexible to operational fluctuations. The base case is feasible with a net present worth of $176,000 and generates a higher net present worth the higher the gas prices get. The optimistic gas price case generates a net present worth of $413,000. And finally, in addition to this, the potential environmental impact reduction of the project supports the recommendation with the reduction of 1.2 tons of carbon dioxide emissions from the brewery each year. Thank you for your time and consideration.